Section 1.5, Transformation of Functions. Learning Objectives. In this section, you will 1. Graph functions using vertical and horizontal shifts. 2. Graph functions using reflections about the x-axis and the y-axis. 3. Determine whether a function is even, odd, or neither from its graph. 4. Graph functions using compressions and stretches. 5. Combine transformations. Figure 1. Credit. Misco, Flickr. We all know that a flat mirror enables us to see an accurate image of ourselves and whatever is behind us. When we tilt the mirror, the images we see may shift horizontally or vertically. But what happens when we bend a flexible mirror? Like a carnival funhouse mirror, it presents us with a distorted image of ourselves, stretched or compressed horizontally or vertically. In a similar way, we can distort or transform mathematical functions to better adapt them to describing objects or processes in the real world. In this section, we will take a look at several kinds of transformations. 1.5.1. Graphing functions using vertical and horizontal shifts. Often when given a problem, we try to model the scenario using mathematics in the form of words, tables, graphs, and equations. One method we can employ is to adapt the basic graphs of the toolkit functions to build new models for a given scenario. There are systematic ways to alter functions to construct appropriate models for the problems we are trying to solve. A. Identifying vertical shifts. One simple kind of transformation involves shifting the entire graph of a function up, down, right, or left. The simplest shift is a vertical shift, moving the graph up or down, because this transformation involves adding a positive or negative constant to the function. In other words, we add the same constant to the output value of the function regardless of the input. For a function g of x equals f of x plus k, the function f of x is shifted vertically k units. See Figure 2 for an example. Figure 2, x, f of x, f of x, f of x plus 1. Figure 2, vertical shift by k equals 1 of the cube root function. F of x equals cube root of x. To help you visualize the concept of a vertical shift, consider that y equals f of x. Therefore, f of x plus k is equivalent to y plus k. Every unit of y is replaced by y plus k, so the y value increases or decreases depending on the value of k. The result is a shift upward or downward. B. Vertical shift. Given a function f of x, a new function g of x equals f of x plus k, where k is a constant, is a vertical shift of the function f of x. All the output values change by k units. If k is positive, the graph will shift up. If k is negative, the graph will shift down. Example 1. Adding a constant to a function. To regulate temperature in a green building, airflow vents near the roof open and close throughout the day. Figure 3 shows the area of open vents V, in square feet, throughout the day and hours after midnight, T. During the summer, the facilities manager decides to try to better regulate temperature by increasing the amount of open vents by 20 square feet throughout the day and night. Sketch a graph of this new function. Figure 3. T, V. Solution. We can sketch a graph of this new function by adding 20 to each of the output values of the original function. This will have the effect of shifting the graph vertically up, as shown in Figure 4. Figure 4. T, V, up 20. Notice that in Figure 4, for each input value, the output value has increased by 20, so if we call the new function s of t, we could write s of t equals v of t plus 20. This notation tells us that, for any value of t, s of t can be found by evaluating the function v at the same input and then adding 20 to the result. This defines s as a transformation of the function v, in this case a vertical shift up 20 units. Notice that, with a vertical shift, the input values stay the same and only the output values change. See Table 1. Table 1. T. V of t. S of t. For t equals 0, V of t is 0, and S of t is 20. For t equals 8, V of t is 0, and S of t is 20. For t equals 10, V of t is 220, and S of t is 240. For t equals 17, V of t is 220, and S of t is 240. For t equals 19, V of t is 0, and S of t is 20. For t equals 24, V of t is 0, and S of t is 20. How to? Given a tabular function, create a new row to represent a vertical shift. 1. Identify the output row or column. 2. Determine the magnitude of the shift. 3. Add the shift to the value in each output cell. Add a positive value for up or a negative value for down. Example 2. Shifting a tabular function vertically. A function f of x is given in Table 2. Create a table for the function g of x equals f of x minus 3. Table 2. X. F of x. For x equals 2, f of x is 1. For x equals 4, f of x is 3. For x equals 6, f of x is 7. For x equals 8, f of x is 11. Solution. The formula g of x equals f of x minus 3 tells us that we can find the output values of g by subtracting 3 from the output values of f. For example, f of 2 equals 1. Given g of x equals f of x minus 3. Given transformation g of 2 equals f of 2 minus 3 equals 1 minus 3 equals negative 2. Subtracting 3 from each f of x value, we can complete a table of values for g of x as shown in Table 3. Table 3. X. F of x. G of x. For x equals 2, f of x is 1, and g of x is negative 2. For x equals 4, f of x is 3, and g of x is 0. For x equals 6, f of x is 7, and g of x is 4. For x equals 8, f of x is 11, and g of x is 8. C. Analysis. As with the earlier vertical shift, notice the input values stay the same and only the output values change. Try it. Number 1. The function h of t equals negative 4.9 t squared plus 30t gives the height h of a ball, in meters, thrown upward from the ground after t seconds. Suppose the ball was instead thrown from the top of a 10 meters building. Relate this new height function b of t to h of t, and then find a formula for b of t. D. Identifying horizontal shifts. We just saw that the vertical shift is a change to the output, or outside, of the function. We will now look at how changes to input, on the inside of the function, change its graph and meaning. A shift to the input results in a movement of the graph of the function left or right in what is known as a horizontal shift, shown in Figure 5. Figure 5. X. F of x. F of x. F of x, plus 1. Figure 5 horizontal shift of the function f of x, equals, cube root of x. Note that h, equals, plus 1 shifts the graph to the left, that is, towards negative values of x. For example, if f of x, equals, x squared, then g of x, equals, open parenthesis, x, minus 2, closed parenthesis, all squared, is a new function. Each input is reduced by 2, prior to squaring the function. The result is that the graph is shifted 2 units to the right, because we would need to increase the prior input by 2 units to yield the same output value as given in f. E. Horizontal shift. Given a function f, a new function g of x equals f of x minus h, where h is a constant, is a horizontal shift of the function f. If h is positive, the graph will shift right. If h is negative, the graph will shift left. Example 3. Adding a constant to an input. Returning to our building airflow example from figure 3, suppose that in autumn the facilities manager decides that the original vending plan starts too late, and wants to begin the entire vending program 2 hours earlier. Sketch a graph of the new function. Solution. We can set v of t to be the original program and f of t to be the revised program. V of t equals the original vending plan. F of t equals starting 2 hours sooner. In the new graph, at each time, the airflow is the same as the original function v was 2 hours later. For example, in the original function v, the airflow starts to change at 8 a.m., whereas for the function f, the airflow starts to change at 6 a.m. The comparable function values are v of 8 equals f of 6. See Figure 6. Figure 6. T, v, left 2. Notice also that the vents first opened to 220 feet squared at 10 a.m. under the original plan, while under the new plan the vents reach 220 feet squared at 8 a.m. So v of 10 equals f of 8. In both cases we see that, because f of t starts 2 hours sooner, h equals negative 2. That means that the same output values are reached when f of t equals v of t minus, open parenthesis, negative 2, closed parenthesis, equals v of t plus 2. F. Analysis. Note that v of t plus 2 has the effect of shifting the graph to the left. Horizontal changes or inside changes affect the domain of a function, the input, instead of the range, and often seem counterintuitive. The new function f of t uses the same outputs as v of t, but matches those outputs to inputs 2 hours earlier than those of v of t. Said another way, we must add 2 hours to the input of v to find the corresponding output for f. F of t equals v of t plus 2. How to? Given a tabular function, create a new row to represent a horizontal shift. 1. Identify the input row or column. 2. Determine the magnitude of the shift. 3. Add the shift to the value in each input cell. Example 4. Shifting a tabular function horizontally. A function f of x is given in Table 4. Create a table for the function g of x equals f of x minus 3. Table 4. X. F of x. For x equals 2, f of x is 1. For x equals 4, f of x is 3. For x equals 6, f of x is 7. For x equals 8, f of x is 11. Solution. The formula g of x equals f of x minus 3 tells us that the output values of g are the same as the output value of f when the input value is 3 less than the original value. For example, we know that f of 2 equals 1. To get the same output from the function g, we will need an input value that is 3 larger. We input a value that is 3 larger for g of x because the function takes 3 away before evaluating the function f. G of 5 equals f of 5 minus 3 equals f of 2 equals 1. We continue with the other values to create Table 5. Table 5. X. X minus 3. F of x minus 3. G of x. For x equals 5, x minus 3 equals 2, f of x minus 3 is 1, and g of x is 1. For x equals 7, x minus 3 equals 4, f of x minus 3 is 3, and g of x is 3. For x equals 9, x minus 3 equals 6, f of x minus 3 is 7, and g of x is 7. For x equals 11, x minus 3 equals 8, f of x minus 3 is 11, and g of x is 11. The result is that the function g of x has been shifted to the right by 3. Notice the output values for g of x remain the same as the output values for f of x, but the corresponding input values, x, have shifted to the right by 3. Specifically, 2 shifted to 5, 4 shifted to 7, 6 shifted to 9, and 8 shifted to 11. G. Analysis. Figure 7 represents both of the functions. We can see the horizontal shift in each point. Figure 7. X, Y. F of x, blue. G of x, equals, f of x, minus 3, red. Example 5. Identifying a horizontal shift of a toolkit function. Figure 8 represents a transformation of the toolkit function f of x, equals, x squared. Relate this new function g of x to f of x, and then find a formula for g of x. Figure 8. X, f of x. Solution. Notice that the graph is identical in shape to the f of x equals x squared function, but the x values are shifted to the right 2 units. The vertex used to be at 0, 0, but now the vertex is at 2, 0. The graph is the basic quadratic function shifted 2 units to the right, so g of x equals f of x minus 2. Notice how we must input the value x equals 2 to get the output value y equals 0. The x values must be 2 units larger because of the shift to the right by 2 units. We can then use the definition of the f of x function to write a formula for g of x by evaluating f of x minus 2. F of x equals x squared. G of x equals f of x minus 2. G of x equals f of x minus 2 equals, open parenthesis, x minus 2, closed parenthesis, all squared. H. Analysis. To determine whether the shift is plus 2 or minus 2, consider a single reference point on the graph. For a quadratic, looking at the vertex point is convenient. In the original function, f of 0 equals 0. In our shifted function, g of 2 equals 0. To obtain the output value of 0 from the function f, we need to decide whether a plus or a minus sign will work to satisfy. G of 2 equals f of x minus 2 equals f of 0 equals 0. For this to work, we will need to subtract 2 units from our input values. Example 6. Interpreting horizontal versus vertical shifts. The function g of m gives the number of gallons of gas required to drive m miles. Interpret g of m plus 10 and g of m plus 10. Solution. G of m plus 10 can be interpreted as adding 10 to the output, gallons. This is the gas required to drive m miles, plus another 10 gallons of gas. The graph would indicate a vertical shift. G of m plus 10 can be interpreted as adding 10 to the input, miles. So this is the number of gallons of gas required to drive 10 miles more than m miles. The graph would indicate a horizontal shift. Try it number 2. Given the function f of x equals square root of x, graph the original function f of x and the transformation. G of x equals f of x plus 2 on the same axes. Is this a horizontal or a vertical shift? Which way is the graph shifted, and by how many units? I. Combining vertical and horizontal shifts. Now that we have 2 transformations, we can combine them together. Vertical shifts are outside changes that affect the output of y-axis values and shift the function up or down. Horizontal shifts are inside changes that affect the input x-axis values and shift the function left or right. Combining the two types of shifts will cause the graph of a function to shift up or down in right or left. How to? Given a function and both a vertical and a horizontal shift, sketch the graph. 1. Identify the vertical and horizontal shifts from the formula. 2. The vertical shift results from a constant added to the output. Move the graph up for a positive constant and down for a negative constant. 3. The horizontal shift results from a constant added to the input. Move the graph left for a positive constant and right for a negative constant. 4. Apply the shifts to the graph in either order. Example 7. Graphing combined vertical and horizontal shifts. Given f of x equals the absolute value of x, sketch a graph of h of x equals f of x plus 1 minus 3. Solution. The function f is our toolkit absolute value function. We know that this graph has a V-shape with the point at the origin. The graph of h has transformed f in two ways. F of x plus 1 is a change on the inside of the function, giving a horizontal shift left by 1, and the subtraction by 3 in f of x plus 1 minus 3 is a change to the outside of the function, giving a vertical shift down by 3. The transformation of the graph is illustrated in Figure 9. Figure 9. X, y. Y equals the absolute value of x. Y equals the absolute value of x plus 1. Y equals the absolute value of x plus 1 minus 3. Let us follow one point of the graph of f of x equals the absolute value of x. 1. The point 0, 0 is transformed first by shifting left 1 unit. 0, 0 shifted to negative 1, 0. 2. The point negative 1, 0 is transformed next by shifting down 3 units. Negative 1, 0 shifted to negative 1, negative 3. Figure 10 shows the graph of h. Figure 10. X, y. Y equals the absolute value of x plus 1 minus 3. Try it number 3. Given f of x equals the absolute value of x, sketch a graph of h of x equals f of x minus 2 plus 4. Example 8. Identifying combined vertical and horizontal shifts. Write a formula for the graph shown in Figure 11, which is a transformation of the toolkit square root function. Figure 11. X, h of x. Solution. The graph of the toolkit function starts at the origin, so this graph has been shifted, 1 to the right and up 2. In function notation, we could write that as h of x equals f of x minus 1 plus 2. Using the formula for the square root function, we can write h of x equals square root of x minus 1 plus 2. J. Analysis. Note that this transformation has changed the domain and range of the function. This new graph has domain, open square bracket, 1, infinity, closed parenthesis, and range, open square bracket, 2, infinity, closed parenthesis. Try it number 4. Write a formula for a transformation of the toolkit reciprocal function. F of x equals 1 over x. That shifts the function's graph 1 unit to the right and 1 unit up.